Hi, this is Dr. Minnick, and this is going to be lab number 2, AC network analysis. So this week we're dealing with a constant frequency AC source at 2 volts peak as opposed to peak. So this is a 2 volt amplitude, and what we're going to try and do is determine what the voltage is here, which should just be the voltage across the source. So these voltages are relative to ground. Voltage at point B across the resistor here, and voltage at point C. We have some resistors, and we have a capacitor and an inductor. This 1 ohm resistor is to make it a little bit easier to measure the current through the inductor, which is another one of our tasks. So specifically, we're looking for those 3 voltages and the current through the inductor, and that's our goal. Alright, so to do this AC lab, we're going to need 2 different pieces of equipment. So we've got a function generator and we've got an oscilloscope. This is now our power supply. This makes an AC signal, and this is kind of like our multimeter. It's a way to look at what the AC signal that's being produced is. So the first thing to talk about is the connections to these. So these are different styles of connections than we've had before. These work on a coaxial cable. So specifically it's a BNC style of coaxial cable. And these cables have one kind of ground that's going around the outside, and then a connection on the inside that's insulated from the one on the outside. So those are the 2 different terminals of this. To see what's connected to what, you can use the multimeter that is connected to these in short detection. So we'll check first of all the negative terminal of this, indicated by the black symbol here, and also by the little negative terminal, little negative sign on the output. And this is actually connected to the outside of the cable. In contrast, the positive is insulated from the outside, but is connected to this tab on the inside. So, to turn on the scope, the power button is up here. We're going to wait for that to fire up. To turn on the function generator, you use the frequency multiplier thing here. So on the bottom left, it's power off, and we can turn this up to go to the right frequency. So, as the scope powers up, first thing we can do is apply the signal from the function generator to the scope and try to look at it. Okay, so there we go. We've got a sine wave that's applied on the scope, and we can change this around to be different waves here. So there's a triangle wave. We can make a square wave. For this, we're just going to need the sine wave, and let's make sure everything is working right. So to get the scope to work, if you're ever stuck and have no idea what to do, then your last resort is to just hit the auto set button at the top and hope for the best. But what we really want to do is understand how things are actually working. So the scope goes on a triggering system. What you can do is set the level for where you want the scope to decide, okay, this is the setting we want to see. This is the start of a pulse, and just moving the actual signal down with this vertical position shift here. By turning this way, you can shift the signal up and down. So putting it here, we've sort of zeroed it in the center. We can change the level that the scope is going to be looking for a trigger at by moving this up and down. So what that does is if we go above the level that the signal's actually at, then we can't capture it unless maybe the signal had a higher amplitude, and now we can trigger. But with this lower amplitude here, no trigger detected. So ways to fix that: increase the amplitude, or decrease the threshold for catching a trigger. Some other things to think about with this device: for this particular function generator, it has the idea to sweep the option to sweep frequency. So if this sweep width setting is not on off, it's turned up, then you can get some really kind of funky patterns showing up on your oscilloscope. So what this is doing is changing the frequency from a lower frequency to a higher frequency. So if you don't want to see that, as cool as it is, then you turn that all the way off. Another thing it can do is set a DC offset, and that's with this knob here. So again, all the way to the left will turn that off. If you turn that on, then we've got a signal which is moving up and down here. So increasing the amplitude will allow that to still trigger and see what's going on. So we're shifting the signal up and down with this offset. We don't need that, so we'll just turn it all the way to 0 and then turn the amplitude back down. Another thing that we want to be able to do with this is set up the signal to have the right frequency and right amplitude for our particular circuit. So if we go back over to the problem itself, we need a 2 volt peak, so a 2 volt amplitude, or 4 volts peak to peak, and we need 4 kilohertz. There's a couple of different ways to set this. First thing you can do is get it to the right kind of ballpark by setting the frequency range on the function generator. So here we're at the 1 kilohertz, so this is at 0.4. What we're going to need to be is probably around 10 kilohertz and 0.4 here. Now to see this show up again, what you can do is adjust the horizontal position with this dial here, and turning that to the right will increase the amount of will sort of widen out the wave. What it's doing is it's decreasing the amount of time per division. So here we're on the 250 microseconds per division. We can go to 100 microseconds per division, and let's just check. So it says here that we should be at about 4 kilohertz, and at 4 kilohertz, the inverse of that, 1 over 4e3, 0.00025. So we expect about 250 microseconds per full wave. So we can adjust the horizontal position here to get that to about the center and count the divisions. So this full wave looks like it takes 1 division, 2 divisions, and maybe around like 2.8 for a full cycle. So that means that we're at roughly 280 microseconds for a full wave. So that tells us that we're probably not at exactly the 4 kilohertz that we are expecting. A better way than just using this setting to set the frequency and using the and counting divisions to see what the frequency is to use the measure menu up at the top. So we'll hit this button, and then what you can do is set up all the different measurements that you'd like to see. So we already have it there on the screen, channel 1 frequency. If you don't have that, I'll show you how to get it. So first click the source button here, toggle this to set the source, change the channel to channel 1, and then toggle that again back to type, and change this around to frequency. So now we're at frequency. We can see the actual frequency right now is 3.87 kilohertz. So we'll increase that a little bit until we get pretty close to 4. Now this has some pretty serious backlash in the adjustment here. So you want to go a little bit past the frequency you want and then let go to get it to go back to the frequency that you're going to end up with. So there we go, pretty much 4 kilohertz. So besides the frequency, the other thing that we want to get to the right setting is the amplitude. And we're going to need a 2 volt amplitude or 4 volts peak to peak. And right now, conveniently, that's measured on this output here. So we've got the channel 1, which is this channel here, the output from the function generator, reporting that its peak to peak is 848 millivolts. So we need that to be a fair bit higher. What we're going to do is adjust with this knob here. So the outside one controls whether or not it's a sine wave versus triangle wave versus a square wave. But this inside one here will adjust the size of the signal. So we can increase that until we get to a 4 volt peak to peak. Now you see, because we're outside the screen range, the voltage peak to peak has this question mark afterwards, meaning that the scope cannot actually measure what's going on here because we're outside of the range. So it says it's 2.03 volts, but it doesn't know. We're off the screen here. So now we need to adjust the volts per division, and that we can do similar to this time adjustment here with this knob here. There's a separate one for each channel. So for channel 1, we're going to use this one, and we're going to turn that to the left to go towards, to make the signal go smaller, which means that we have more volts per division. So now we're at 500 millivolts per division, and there we'd expect an amplitude of 2 volts to take up 4 divisions. So that would mean 1, 2, 3, it should be about right at the top. If we go here, one more, then now we're at 1 volt per division. That means it'll take up 2 divisions when we get to a 4 volt peak to peak or 2 volt amplitude. So let's increase that a little bit more. And there we go, 4 volts peak to peak. Okay. So now we've jumped to another lab bench just to show you what the other style of function generator looks like. This is a digital function generator, and the scope's on the other side. So this is still the scope, but now this is the function generator. You can turn this on with the power button, and then we've got similar functionality to the other one. So this can decide whether you have a triangle wave here with this button, square wave, sine wave, and it adjusts the frequency by the big range indicator at the top. So in the 10K range, 1K range, and then you make precise adjustments to that with this dial here. And you can read on the top what it thinks the frequency is, and also measure what the frequency is over here on the scope. So here we've got 982 hertz measured, and the scope is measuring between 982 and 984. Okay, now the other thing is this one also has a DC offset. It's a little, and an amplitude adjustment. So amplitude adjustment over here, and DC offset here. Now at first it looks like the DC offset isn't doing anything, but to fix that you just pull the tab out, and now it will listen to the DC offset that you're setting. Alright, so now we've got our circuit ready to build. First let's double check that the breadboard terminals are connected to what we think they are. So the negative should be connected up to the negative here. Yep. And the positive should be connected up to the positive rail. Alright, we're good to go. Now for this circuit, it's going to be easier if to visualize if we make use of the bottom negative rail and the top positive rail for the other side of the voltage supply. So let's go ahead and use a jumper wire to connect the negative rail from the top to the bottom. Next part, we need to get the resistors measured. So up on our multimeter, we'll turn off the sound to make that a little bit less obnoxious while we're measuring things. And now we're on the 200 ohm range, which is going to be the perfect range to measure the 3 resistors that we have, 100, 68, and 1. So I've already gotten these resistors out of the drawers there. Let's just measure up and see which one is which. So this one is a 1 ohm resistor, and we're going to need that to be connected to the ground on the circuit. Let's use that ground. That's good. And connect that over there. Next one looks like it's the 100 ohm resistor. We're going to need this one to connect also to ground and to what's going to be our terminal B there. And that means that by process of elimination, the last one should be the 68 ohm. Let's double check that. Yep, looks pretty good. So while you're doing the lab, it would be a good idea to write down the numbers themselves on the paper so that you could check the exact values later. So we'd want to go back and do the 100 ohm again. We'll see 66.8 there. This needs to be connected to the other side of the 1 ohm, so we'll jump into this spot there, and then we'll need to put that close to the other connection of the 100 ohm. So let's just double check the 100 ohm resistance value and write that down. So 97.6. And we'll put that in a spot. Let's actually lay that up like this, and you'll see why in just a moment. So the other components that we need are an inductor to bridge between these two top connections, the top of the 68 and the top of the 100, and we'll need a 1 microfarad capacitor to go from this junction up to the high voltage of our supply. Alright, so for the inductor, The inductor looks something like this. This is our 100 millihenry inductor. You might also have one that looks like this style. So in this one, you would connect this terminal to this terminal is 100 millihenry, and it actually has two on the one little piece there. This one is just two terminals, so it's 100 millihenry between them. So we need to connect that across the top of the 68 ohm and the top of the 100 ohm. So we'll do that on the breadboard like this. The probes are the right spacing to fit a little bit apart with a gap of just kind of one between them. So we'll put that in there. And then we can connect the 1 microfarad capacitor from that junction here at B to the positive terminal there at the top. So we'll do that. And there we go. So circuit looks all set up. To actually apply power to this, what we're going to need to do is change our function generator here to be placing the voltage and current across the into the two terminals at the top. But before we do that, what I'd like to do is keep it on the scope while we're doing this and point something out on the scope. So we'll take the negatives here and just connect the bottom terminals. And the other thing we're going to do is take the positives and connect this, and watch what happens to the signal as we do that. So you'll see the signal has actually dropped down a fair bit as we've connected it to this circuit. And the reason for that is the output of this circuit here, if you look really closely in on the function generator, you can see it says 50 ohms out. So that means that the impedance of this device is 50 ohms. And if you put this across this other circuit here, which turns out to have a total impedance that's comparable to 50 ohms, then we get a voltage divider where not all of the output of this shows up across the actual circuit. That wasn't the case when we were applying it to the scope, because the scope has an impedance of about 1 mega ohm, so it's much higher impedance on that than it was across the device here. So that means we need to readjust the amplitude here to get back up to 4 volts as our peak to peak, and that's pretty good. 4.16, 4.08, that's pretty good. Okay, so then the next thing is to hook up the scope probe here. So we'll connect this to channel 2. And this has 2 different connections on it. It has an internal one, which is connected to the inside pin of this coaxial cable, and it has a clip, which is connected to the outside pin of the coaxial cable. You can put the scope probe on 2 different measurement modes. So you can put it on a 1x mode or a 10x mode. If you put it on the 10x mode, then it cuts down the signal that it's measuring by a factor of 10 before it shows up on the scope. So you're going to see a much smaller signal there. The other thing is the outside terminals, so the ground pins of the scope, are connected to each other, and in fact connected to instrument ground through a DC stopping capacitor and a 50 ohm resistor. So that means that whenever you have this hooked up to something that's measuring AC output by the function generator, you have to set it up so that your ground of this is connected to the ground of the function generator. You can't do a relative measurement like you could do with the multimeters. So it should, in theory, be perfectly fine for you to switch these 2 connections on the scope here. But in reality, that it doesn't work out quite as well when you're measuring things. So the next thing to do is to adjust the amplitude back up on the function generator to get to our 4 volts. So we'll do that, reading off the peak to peak, 4 volts, there we go. And now we can hook up this probe and measure what's going on, what the voltage is at different points in the circuit. So we'll make sure that the probe is on the ×1 mode, and we can go to the channel menu and make sure that it knows the probe is on that too. If you want, you can have the probe in a higher impedance mode. You just have to set the menu here to tell the scope about it, or your measurements are going to be too small. So we'll leave that on 1x for now, and we'll connect this up to wherever it is that we want to measure in the circuit. So first thing we can do is just double check and take the measurement at the top here, and that should be the same as the other measurement. So we see that we've got channel 2 turned on. If channel 2 has disappeared, then you can hit the menu button twice and that'll toggle the display of that. You could also turn channel 1 off, now you don't see anything. Channel 1 now displayed again. Turning on channel 2, then we'll turn down the volts, turn up the volts per division, so turning down the size of the signal by rotating this to the left. And we have a DC offset. You see the center point of channel 2 is lowered down. You can move that with this vertical position adjustment, moving that back to align with channel 1 there, to be both centered around 0, and then reducing the amplitude, and they should overlap, and they do. If we want to take a measurement somewhere else, then we can connect that, say, to the other side of the capacitor, so this would be point B. And easy way is to get the measurement mode, channel 2 peak to peak, we see 3.72 volts. And that's one of the things we want to do, is the amplitude measurement of that. So now let's jump back over to our theoretical parts and see what voltage we expected to get there. So if we go into our analytical solution here, we see that VB is calculated as a complex number here, and then we take the absolute value of it times 2 to look for the peak to peak, and that's this. So we should get 3.767, so 3.72, pretty close. If we want to know what the voltage at point C is, then we'll disconnect the scope from there by kind of pulling down on this to release it, and then connect over on the other side of the inductor, and this is now point C. And here the signal's a fair bit smaller, so we've got 240, 280 millivolts. We can rotate this to the right to make the signal big enough to see it. It's a lot smaller of a signal, so it has a fair bit more noise in it. And VC, according to our theory here, should be about 100 millivolts peak to peak. And you can see now that we've magnified it enough to see, we're getting close to 110 millivolts peak to peak, so that's pretty good. So the reason we can measure anything at all here with when we've only connected one terminal, like what voltage is it measuring it relative to, is because the scope is actually connected inside. So the ground of channel 1 is connected to the ground of channel 2. You could turn off the scope, disconnect things, and then measure that with the multimeter if you want to see the impedance between those two channels. However, to get a cleaner measurement, you usually want to use the ground right here to take advantage of the coaxial cable all the way along and cut down on the noise. So we can see that for this small signal, very noisy measurement when we connect this ground to the ground on the breadboard here. Watch the noisiness of that signal cut down, and that's a lot cleaner there. So we can get a much better measurement. In fact, it turns out that the peak to peak is lower than we were measuring before, and that just changed by cutting down the noise by connecting the ground cable there. So the last part is to look for the phase difference in these two measurements. When we did the analytical solution here, we could take the, let's say for VC, we've got the rectangular form of the complex number here, and then by taking the argument of it, we get the phase difference. So this is in radians. To figure out what this, to compare this to the measurement that we're getting on the scope, we need to convert it into fractions of a cycle, or even a time difference ideally. So what we'll do is from the argument, we'll now take that divided by 2 pi, and that tells us 0.18, so 18% of a full cycle. And in terms of delta time, we'll take that and multiply it by the period, so 1 over the frequency, and that will convert it into the exact time difference that we should be looking for. So we expect that the voltage at C relative to the voltage at A is delayed by 46 microseconds. Okay, so let's look at how we would measure that with the scope. So first of all, we expect that VC, so which is on our channel 2 here, this one, is the one that's a little bit after the other one on the scope. So let's, if we look at the scope here, we can turn off channel 2 and see that, yeah, that's the one that's delayed a little bit. That wave is a little bit after the other one, so time is increasing from left to right across this. And so the one that looks bigger, which is actually just because we've magnified it a lot, it's a much smaller amplitude actually, is delayed a little bit. So to figure out exactly how much this is delayed, we can increase the time scale here and then use cursors. So what we'll do is we'll hit the cursor menu here, and you can change it between off with the type button and voltage and time. We need time cursors for this. And now once you're on the cursor menu, these two signals, these two knobs here at the top, rather than adjusting the voltage up and down, what they'll do now is they'll adjust the two cursor positions left and right or up and down. So a good way to take this measurement is to look for where the signals cross the axis, and then it will tell you the difference between the two cursors. So it's saying 44 microseconds right now, and once again we expected about 46 microseconds. So that tells you the phase difference is pretty much what we expected as well. You can get a better measurement by increasing this even more on that scale, maybe turn up the volts per division to see more clearly where they cross the axis, and sort of zooming in on that, we end up with a measurement which is now about 43 microseconds. So those are ways that you can make this measurement a little bit more precise. So that's it. Thanks for watching Lab 2. I'll see you next time.